Hey everybody, we are working through your textbook today. We're starting this new kind of chapter. It's called I Want to Believe, but what it's really about is imaginary and complex numbers. And hey, I am starting off on page M1-93 and really looking at this page right here. So this is page M1-94. So I'm not going to go through a lot on this getting started page, but a few things that I want you to notice is all these quadratics. They do have these key features. They've got zeros, y-intercept, axis of symmetry, and a vertex. So like on this first one, you know that the vertex is right here, and we have this axis of symmetry that's cutting our parabola in half. If we continue this function, eventually there will be a y-intercept. And then for concavity, you know that this is concave up. On this function, the second function, again, we have a vertex. It's easy to kind of sketch in the axis of symmetry. It has a y-intercept right here. It has x-intercepts. Fantastic. Now this one is what we're really going to be focusing on for the next week or two. So again, you know, we have a vertex, which also happens to be its y-intercept. The axis of symmetry is right here. It's literally just the y-axis in this case. It's concave up, but the big thing here is we don't have any of these. We don't have any x-intercepts on this. So what you would write on something like this is there are no real solutions. There are no real solutions on this function or for this function. So for what do they have in common? Well, they all have these key features, but one thing that's different is the amount of x-intercepts. This one has no real solutions. This one doesn't have any x-intercepts. The parabola never crosses the x-axis. This one, we have two x-intercepts. We cross right here and right here. We have an x-intercept at 0 and at 6. This one is kind of interesting as well. It has an x-intercept right here. And hey, so whenever a parabola comes down and bounces off of that x-axis, whenever it bounces off of this, that's called a double root. You get the same solution twice. That is called a double root. You get the same value, again, just 2 times. It's called a double root. You get the same solution twice. This one, you get 2 distinct solutions. And if it never crosses the x-axis, you have no real solutions. And again, this is what we're really focusing on, is a situation like this. It's going to require a lot of work before we're able to actually solve these. So yeah, let's move on to the next page here. The number I. It's a very interesting number. So I is short for imaginary. So I represents an imaginary number. And it's looking at that last function there where I told you there's no real solutions, but there are imaginary solutions. And that is, again, what we're going to try to end up finding by the end of the week, or the end of this kind of like, you know, unit topic thing. There are imaginary solutions. No real solutions to this, but there are imaginary ones. And so, hey, this number I, the imaginary number, is going to help us get there. And so the number I, it's a lot like pi. You know that pi, that irrational number that goes 3.1415 something something. It keeps going on forever. It's just another number. So think of I as literally being a number. And this is why I exist. It's when we have a situation like this. All right, so what did Mark do wrong? He was trying to solve this to find the zeros, subtracted 1, and then he did the square root of -1 and said that the solution there is positive or -1. So that's actually not true. If I was like actually doing this, if I was solving this, x squared equals -1, you know this step, I did the square root of x squared to cancel out the square, and I did the square root of -1. Let's see what happens on a calculator. If I try to do the square root of a negative value, if I do the square root of -1, I hit enter, I get an error message. Error, I have a non-real answer. Square root of -1, it's not a real number. Again, it's an imaginary number. So we'll just write it kind of like Elena did over here, plus or minus the square root of -1. All right, so what did Mark do wrong? You cannot take the square root of -1. Consider Elena's solution. Does the solution fall within the real number system? And again, that's no, because if I try to do the square root of -1, I get an error message. And it's really easy to see on the calculator, right? I get some non-real answers. So does it fall within the real number system? Not so much. This is an imaginary number. So not a lot to do on this first page. Let's go to page or the next page, M1-96. All right. So in order to calculate the square of any real number, there must be the way to calculate the square root of a negative number. So mathematicians came up with a way of getting around this. We need to find a way to square root a negative value. We need to find the way to square root a negative number. And so how we do that is the number I. So this is really important right here. Really important. The number I, crucial for Algebra 2 here. And again, like I already said, it's kind of similar to pi. You know that pi is literally a number. When you see pi, it's not a variable, it's not going to change. Pi is a number. So I have the same thing for I. Now this is really how it's defined. I squared equals -1. I want to write that down just to reiterate that. I squared equals -1. That's the easiest way to define it. And I'm pretty sure that's even a question on the ACT when you take it. I squared is -1. Now that said, if this number squared equals -1, then hey, what's the value of just I? So if I square root this to get rid of the square, I square root this side, I is equal to the square root of -1. So it might not be clear why that's going to help us out yet, but we will get there. So recall the function that we looked at the beginning of this video, p of x equals x squared plus 1. Write the zeros of the function in terms of I. So what we're doing is solving this. X squared plus 1 equals 0. Remember, to solve a quadratic or to find the zeros of a quadratic, you have to set the function equal to 0. And then if I start to solve this, I'll subtract 1 from either side. X squared equals -1. And then when I take the square root here and the square root there, x is going to be equal to positive or negative. And remember, the square root of -1, how we're going to write that from now on, the square root of a negative number is I. Square root of -1 is I. So hey, those would be the zeros, plus or minus I. So functions and equations that have solutions requiring I have imaginary zeros, or of course, this can also be called imaginary roots. So we don't have real solutions to this function. We have, again, imaginary solutions. We have imaginary zeros. So how can you tell from the graph of a quadratic equation whether or not it has real solutions or imaginary solutions? So the way to tell is, does the parabola intersect, like cross, does the parabola intersect the x-axis? If yes, if it does intersect the x-axis, you will have real solutions. If no, if it does not intersect the x-axis at all, then you will have imaginary solutions or zeros. So just look at a graph and tell if it crosses the x-axis. That'll let you know if you have real or imaginary solutions. Do you think you can determine the imaginary solutions by examining the graph? So looking at like this graph, it does not cross the x-axis. And we had, of course, no real solutions. These ones were imaginary. And you cannot tell just by looking at a graph where the imaginary solutions are. That is impossible because this coordinate plane has real numbers only. This graph does not include imaginary numbers. So we cannot tell where the solutions are. No coordinate planes that we're graphing on Coordinate planes do not include imaginary numbers. Imaginary numbers. All right, fantastic. So that's it. Let's keep moving on here. We're going to be looking at complex numbers. So hey, we know now that there's different types of numbers, right? There's this chart is honestly very, very helpful. So one thing to consider here is this is like the hierarchy right here. All numbers are complex. All numbers are complex. No matter what, your number will be complex. Now, there's different stuff down here, of course, right, that we're going to be looking at. So natural numbers are complex numbers, but like to be more specific, natural numbers, I like to think of that as things that you can count on your finger, essentially. So a natural number, like we have 1, 2, 3, 4, 5, those are all natural numbers, things that you can count. Whole numbers are almost the same thing. So a whole number would be any positive value that doesn't have a decimal. Integers, kind of the same thing there. An integer can be a positive number or even a negative number, like that's all fine. Now, rational numbers are things that you can express as a fraction. So like a rational number, like an example could be 3 divided by 8. That's a rational number because it can be expressed as a ratio, right? Irrational numbers are things where, like pi is an irrational number. Anything where a decimal doesn't end. If I did something like maybe 7 divided by 22, see how I just get this number that's never going to end? That is irrational. So hey, real numbers, this is really what we kind of want to focus on. Real numbers are written in this form where b is equal to 0. So what this means is you don't have an imaginary part to it. So a real number could be like anything with like, I don't know, 3.86 is a real number. 2.9 repeating is a real number. Anything without an imaginary part to it. Imaginary numbers are the exact opposite of a real number then. Imaginary numbers have that imaginary part, okay? So an imaginary number, like 7i. If you see an I, your number's imaginary. And imaginary numbers, again, they just come up from like, hey, so the square root of negative 49, square root of negative 49, the square root of something negative is imaginary. So this is how you get 7i. The square root of 49 is 7, and the square root of something negative is imaginary. So complex numbers are written in this form. Again, all numbers are complex, but really what complex numbers look like are combining these two things, combining a real number with an imaginary number. So a complex number will be written like this, maybe like 3 plus 4i. That's what a complex number is going to look like in this course. If I just had 3 or I just had 4i, again, those would also be complex. It might seem confusing, but once you do some problems with this, it really gets to be like not so bad. So let's go on to the next page and look at these statements. So if a number is imaginary, if a number is an imaginary number, then it is always, sometimes, or never a complex number. So remember, all numbers are complex. So if it's imaginary, then it is always going to be complex. Always, all numbers are complex. So if a number is a complex number, then it is always, sometimes, or never an imaginary number. So hey, if it is complex, it doesn't necessarily have to have an imaginary part. Like, here's an example, 3 plus 2i. That has an imaginary part. That is an imaginary number and a complex number, but I could have also had a number like this, just 3. This one is not imaginary. It's just a real number. So if a number is complex, then it is sometimes imaginary. Sometimes imaginary. All right, so for part C, if a number is a real number, then it is always a complex number. If a number is a real number, then it is All right, so if it's a real number, it's not going to have an imaginary part. If a number's real, then it is not imaginary. So this would be never. Then our last one, if a number is complex, then it is sometimes a real number. That would be sometimes a real number. Okay, so like an example, right? Just going back to this would be if a number is complex, it's sometimes a real number because I could have just an imaginary part. So it's complex, but since I have an imaginary part, it is not real. Okay, for part 2, you use the diagram on the previous page to list all number sets that describe each number. So this will take a while, and I'm not really going to go through all of these, but so like 3, that's something that you can count. So that would be a natural number. That would be a natural number. It would also be rational. I should have kind of skipped a few. It's also a whole number. It's also an integer. And it's real. And it's complex. A lot going on with that number. So B, I'm doing the square root of 7. So the square root of 7, I get this decimal that's never going to end. So it is irrational. Irrational numbers have those decimals that are never going to end. It's irrational, but it's still real. And of course, all numbers are complex numbers. All right, hey, so this one, so they have an imaginary part. It's imaginary. There's an imaginary number. And also it is complex. All right, so 7/8, like you can't really count that on your fingers, so it's not natural or a whole number. It's not an integer, but it is rational. It's expressed as a ratio, that's fine. It's rational, it's real, and it's complex. Okay, and then this one, so it's got 2 parts to it. It's got a real number and an imaginary number put together. So it's not only imaginary, it's not only real, that is a complex number. It's imaginary too because it does have an imaginary part. All right, so let's move on. This is really like the bulk of what you should be able to do today. So we want to be able to rewrite square roots of negative numbers as imaginary numbers. And it works you through a good example right here of how to do that. So we all know that the square root of 25 is 5, and the square root of something negative is imaginary. So let's go through a couple practice problems doing that. So rewrite each expression using I. So hey, the square root of -4. Well, that can be rewritten as the square root of 4 times the square root of -1. That is algebraically equivalent. The square root of 4 is 2, and the square root of anything negative is imaginary. So the square root of -4 can be rewritten as 2i. Awesome. So part B is going to be going to require a little bit of work here. This one is not so easy. So square root of -12. We want to, well, we can make this one kind of easy, I guess. Let's do the square root of 12 times the square root of -1. All right, so we're going to have an issue on this one because the square root of 12 is irrational. And we don't want to approximate on this. So what we're going to do is just rewrite this as the square root of 12 times I. So we can simplify that one further, but let's just skip that for now. So square root of 12 times I. That's it. That's how you would simplify that one. For part C, 5 plus the square root of -50. So let's rewrite it as 5 plus the square root of 50 times the square root of -1. All right, so we can do more to this, and let's actually do it this time. So 5 plus the square root of, so we can break down 50 further. Square root of 50 is the same thing as the square root of 25 times the square root of 2. And then again, the square root of -1 is I. That's literally what it means. So this is what I'm saying. The square root of 25 is 5. So we'll have 5 plus 5 times the square root of 2 times I. Kind of a goofy looking complex number, but that is how you would rewrite it. All right, so part D, let's write it out like this. 6 minus square root of. All right, so we can break down 8 as well. 8 can be the same thing as the square root of 4 times the square root of 2 times the square root of -1. So you should be able to get back to what's inside of your radical sign. 4 times 2 is 8. 8 times -1 is -8. All right, and then this is all being divided by 2. All right, so now I've got 6 minus, well, hey, the square root of 4 is 2. The square root of 2, I'll do it on my calculators just to show you. Square root of 2, not what I wanted. The square root of 2 is this irrational number. So again, if it's irrational, we don't want to rewrite it. Let's just leave it as a root. So this will be square root of 2. And then we know this, right? The square root of -1 is just I. And again, this is all being divided by 2. All right, so since it's all being divided by 2, 6 divided by 2 would be 3. And then think of the square root of 2i as like a variable. It's just being x. So I'm cutting the 2 in half, not all of this stuff. So I'm going to rewrite it as the square root of 2i. So I did 6 divided by 2 for 3, and then -2 divided by 2 kind of just cancels each other out. So I got 3 minus the square root of 2i. So on your assignment today in Schoology, this is really what I want you to be good at. Just rewriting things like this. And I guess I could do part B a little bit further, like I was saying, because we could have done part B. Could have done part B like this. The square root of 4 times the square root of 3 times the square root of -1. So I've got 4 times 3 for 12, 12 times -1 for -12. All right, and then you can simplify this thing. So it's factoring out a perfect square. Square root of 4 is 2. So I've got 2 root 3 I. Square root of -1 is I. So that would have been a more simplified approach, breaking this down. But really what I'm worried about is just noticing that the square root of something negative is imaginary. That way, we can start solving quadratic equations that look like this. This is our goal, be able to find imaginary solutions when you have a quadratic equation that looks like this. All right, so I've been rambling for a very long time. I'm going to go ahead and end this video. Thanks, everybody, for watching. Bye-bye.